As we continue to learn about complex numbers, I'd like to reintroduce the Argand diagram. I talked slightly about it as I mapped out how we were going to teach complex numbers. So as I said then, the Argand diagram is a replacement for the number line. The number line we've used for years, where we represent numbers, 1, 2, 3, then we added in minus numbers, -1, -2, -3. This is how we represented the numbers we use in our everyday lives. 1, 2, -5. We don't use minus too much in our everyday lives, but we owe people money often. So it was a very useful tool, but it wasn't enough to deal with complex numbers. Complex numbers are, as they suggest, complex. They are made up of a real part, which is this line here, this classic number line, which is identical to this real number line here. This is identical. If you want to represent the number 2, it is right here. The number 3, the number -2, and in fact the number 0 here in the middle. Let me clean that up here. The number 0 right here. They can all be represented. But we've introduced complex numbers now. For example here, w is equal to 3 plus 4i. To represent that is a challenge. We need this two-dimensional plane to do it. So how we do it is we keep the real line here and we add in an imaginary line. And I'll go ahead and show you how to draw w first of all. Then I'll show you how to draw a w with this line above it. That's the complex conjugate we talked about in the last video. I'll talk about again slightly, just as we're drawing it. Then I'll go ahead and find the modulus. The modulus of w. It's really helpful to have the picture to get the modulus. We don't need the picture, but it's really helpful to have the picture to talk about it. And then finally I'll talk about the argument of w. Again, it's helpful to have the picture, but not necessarily needed. So let's jump right in. Let's go ahead and draw w. To draw w, we simply look at the real part, is 3. Here's 3 here. And then we look at the imaginary part, +4. So we go to 3 and we go +4 on this imaginary line here. And where they join each other looks to be about there to me. So that is the number. I might have said point a moment ago, the number w. And I'd like to point, I definitely said point that time. I'd like to talk about the difference between the xy axis, xy, and the real imaginary. They work very similar. You put these literal points on the same way, but they're not the same. And I'd like to just point, I can't stop saying point. I'd like to talk about that. In an xy axis, we use two numbers to represent a point. And I did mean to say it that time. To represent a point. In this, we're using a point, I guess, but to represent a number. It's one number. These are not two numbers put together, 3 and 4, to get this point. This is one number. In fact, if we wanted to draw an xy axis where two numbers were put in, we would have to use this one number on this two-dimensional axis combined with another number on another two-dimensional axis and get 4 dimensions. So what we do in an xy axis, we use this number line and then we represent another number line like this and we get our two-dimensional plane. Unfortunately, I cannot visualize how to combine 2 dimensions with another 2 dimensions. It's too difficult. I can do 3 dimensions. We live in 3 dimensions, but 4 dimensions, 4 physical dimensions, I can't visualize it. So we're not going to be doing xy axis. We can do the maths of it actually. We won't be doing it in a secondary level course, but it is possible, but we can't visualize it. But let me continue to answer these questions here. W, the conjugate of w, I can go ahead and write that out. The conjugate of w is equal to 3 minus 4i. It's very simple to do. We just change the number of the complex part, of the imaginary part, I should say. Change the number of the imaginary part. And that, again, should be quite simple to draw. It is +3 on the real line, -4, this should be a minus number there, -4 on the imaginary line. And we get another point there. We get the conjugate of w. Now there is some interesting combinations, the conjugates, they are a mirror image of each other. But we'll talk more about that maybe. I think I'll do a video. Maybe not do a video on the geographical representation of these complex numbers when we multiply them, when we do conjugates, when we square them, things like that. Okay, and next we'll move on to the modulus. Let me write out how to spell that. The modulus of W is, we just represent it by these two lines. Like the absolute value, and it would be similar to the absolute value because it won't matter if we have a minus number or a plus number, and we'll see that with these. We'll do the modulus of both of these. In fact, the modulus of W is geographically, I think, is much better to think of. It is the length from this point to the origin. The length from this point to the origin. And that's quite easy to get because I'd like to remind you, you have a triangle here that is 4 high and 3 wide. That's going to get a bit confusing, that 3 there. But 4 wide, let me put it here, 4 high and 3 wide. So you actually have a Pythagoras theorem. So we could just say the square root of 3 squared plus 4 squared. 3 squared plus 4 squared. You don't have to draw a picture every time. And that's simply equal to 9 plus 16, which is the square root of 25, which is equal to 5. The modulus of W is 5. And we're going to use that quite a bit. You'll see why in a few videos, but we do use that quite a bit. I won't talk about it now. I'll talk about it in a few videos. There's basically another way to draw points. I guess I will talk about it now. There's another way to draw points. Instead of going 3, 4 and getting this point, we go angle. We get the angle here, which you're going to see when we do the argument. We get the angle and then we go out a length. So that's where modulus really comes in handy. Let me also get the modulus of the conjugate. Where's the conjugate? Here's the conjugate here. And now we don't actually need to use the picture. I'll just show you how to just use the numbers. This is still equal to this number squared, 3 squared, plus this number squared, which is minus 4 squared. But I would point out geographically that's a little different. Geographically we have a different triangle, very similar, that is still 4 high and 3 wide. So if you went geographically, you might write 3 squared plus 4 squared. But if you went just from the numbers here, you might go 3 plus minus 4 squared. But this should still equal 20 square root of 25, which still equals 5. These are the same. The modulus of these two are the same. And that's why we use, I guess, I'm not sure about this, but I assume that's why we use the similar similar to the absolute value. Because if we got the absolute value of a minus, it doesn't matter minuses or pluses. We should get the same length whether we change the 3 to a minus or a plus or the 4 to a minus or a plus. That'll just get a point out here and a point out here. Okay, let me make a little bit of space here and I'll go ahead and do part 4, the argument. We'll introduce that. So that's spelled, I believe, like the English word. Let me check. The 4 would be the, let me write 4 again. The argument, yeah, I think that's spelled correctly. The argument of W is, and we write it like this, A or G of W. Fairly simple, obviously it's short for the argument. And now the argument again is very useful to see visually. It is the angle we make with an x-axis. So here's the point W, and if we were to draw a line, which I've already done here, it is the angle we make, sorry, I said x-axis, I'm really sorry. I will be slipping up like that multiple times. It's the angle we make with the real axis. So it's this angle in here, let's give it a symbol here, theta. It's this angle here. But I will point out a few things. We always start at the x-axis and we go plus. So this number, this would be plus pi would be here. This would be about pi over 2. I'm using radians. Or if you want angles, it'd be 45 degrees, 90 degrees. So pi over 2, pi. And we go plus. And We have an option though for when I do the complex one. We can stay, I like to just stay starting here and going plus. So I like to just go all the way around and find this angle around to here. And let me put that in. This angle here. I like to find that for this one. But you have an option. This angle is identical to minus this angle. Let me put that in. This angle here being, let's write phi, and we'll put in minus phi here. So you could just go ahead and, let's say this is, it's not 45, but it's about, let's see, it's about, I'd say 50 degrees or so. So if this is plus 50, we call this one minus 50. Or we could call it plus 310. They're about, that's the same thing. Let me go ahead and do it with a bit more maths. Because how we get this angle, we use trigonometry. And that is the tangent of this angle is equal to the opposite divided by the adjacent. So we could get this angle in here, this theta. Let's write this first. The argument of W is equal to theta. Let's just to keep it simpler. So theta here, and theta, or let's say tan of theta, is equal to, what is it? It's 4 divided by 3. So, or to put it another way is theta is equal to the arctan, or the inverse tan, of 4 over 3, which that's equal to the argument of W. So we can put that in a calculator, get a number, but it's also fine just to leave it like this. And then let's get the argument of the conjugate, and that's equal to, similarly, it's just the inverse tan. The inverse tan, in this case, it is still 4 height, 3 width, if we use geographically, 4 over 3, which is the same number. That's a problem. So I would have to notice, if I'm using the image, I would have to notice that I'm going minus. I am going minus down here. Or if you, as you get better with, we haven't done trigonometry yet, so I'm trying to limit my talk about it. But as you get better, you will come to realize that minus this number is the same as plus this number here. But either way, this will be minus the inverse tan of 4 over 3. And that's the arguments that's the modulus, and that's how you draw points on an Argand diagram. Thanks for watching, and any questions you have, write them below and I'll do my best to answer them. And next video we will be going back to an old favourite, quadratic equations, but this time with complex numbers involved. Thanks for watching, and goodbye.